My name is Scott Shadley. I'm the VP of Marketing of NGD Systems, a member of the Board of Directors, and I'd like to welcome you to SDC 2020 Virtual Edition. For today, I wanted to spend some time talking to you about a unique and new and innovative technology called computational storage. For purposes of this particular session, we're going to spend our time on edge use cases. There's lots of ways you can deploy the technology, and we've highlighted several of these in past years, and I want to continue to drive forward the technological advances of computational storage with you. So as we walk through this particular presentation, I thought it would be fun to stick with kind of the who, what, when, where, why, and all those good W's. Got lots of questions. We've got some time together today. I want to keep you engaged. So the opportunity to talk to you in that form is just kind of what we wanted to go with today. So who is NGD Systems? What is a computational storage drive? When is it ready for deployment? Where are the examples available? That's going to be the fun one. And of course, why is it important to the marketplace today? These are the types of questions that we want to answer, and I'll do my best to walk you through each of these in an innovative, interactive, and hopefully engaging way. So first off, I get to brag a little about what we do. So NGD Systems has been around since 2013, and we designed and developed the effort around the company for purposes of computational storage. It's not something new. It's something that's had its attempts in the past. We took time, set aside resources, and decided to rethink how to get the next generation of storage forward. We've been shipping products worldwide since 2018 in production. You can see images of our particular drives there on the right-hand side. And we have the largest capacity, lowest power NVMe drives on the market that happen to also offer the ability to do computational storage resources within those devices. We did that because the world is growing in data that we generate, and we need to find a place to store it, and we have very storage-intensive applications. So what can we do to fix that problem? Well, stop moving as much data, focus on energy efficiency. We have a finite amount of power. It's becoming a big problem. And of course, the capacity footprint. You need to be able to do more with less, especially as we talk about edge deployments. So NGD Systems has been around for some time. We have some key market segments that we're going after. We focused heavily on hyperscales, content delivery network platforms, and especially in this case, we're going to spend most of our time today talking about use cases for AI and edge deployments. So when we think about the technology and computational storage and what we have to offer and what we can do with this technology moving forward, I wanted to kind of take a fun gander at where we are, where we were, and where we can go. So historically, we are on the left-hand side of this page, and you can see we have pain points. There's a physical space problem, especially in certain areas like Europe. There's very space-constrained opportunities for data centers. The amount of available power, carbon neutral, has become the new term for 2020 alongside our friend the pandemic. Scaling mismatch. We have these amazing CPUs, some really cool DRAM, and what do we do about storage? We just make it a little bit faster, PCIe Gen 4, Gen 3, all that kind of fun stuff. It's not quite enough to get where we need to. All we're doing is creating what I've nicknamed the bottleneck shuffle. So we're sitting today with the past on the left. We're sitting in the present with what now computational storage can offer, and it's also the future of this technology for all of the storage architectures that exist today. Why is it of value to us at this point? Because when we think about it, we're bringing in a smaller footprint because we have higher capacity solutions and we're not having to scale servers in the same way to get the same kind of compute resources. We're lowering the power consumption because we're using the CPUs for what they're really needed to do and not simple storage-related applications that can be offloaded into each and every one of the parallelized storage devices, which helps with the distributed processing. And of course, you're going to end up with some results that are going to be much more efficient, either from a power or from a performance point of view. And so that when I think of it from that perspective, when we kind of take out the idea of the past, the present, and the future, I look at it more of, let's take the track of innovation. We need to be able to move the technology forward. We need to have great architectures, and we need to solve today's problems with tomorrow's technology, and that's what computational storage is bringing for us today. So as I mentioned, NGD created a product, and we've decided I classified it as optimizing the solution or creating the right way to solve this problem. We did that by creating an ASIC-based solution. So we do have a 14-nanometer ASIC controller, and we wanted to make it as simple to use as possible. So it has everything your standard NVMe device has, including a very modular firmware base and the opportunity to work with any flash vendor and any media. So again, we're an independent startup, so we don't have the dependencies upon a media that we generate, but we can work with any media that you'd like to from a technology perspective. So what we did differently within this particular computational storage drive is we took an NVMe device. You have your standard media controller. You're talking to your media. You're doing all your normal stuff that you want to do with that. And we've added in what we classify within the computational storage space within SNIA as a CSP, a computational storage processor. In the case of our particular product, it's an ARM-based application core that is sitting inside that ASIC alongside the media controller. So it's an all-in-one solution, turnkey, simple, and seamless. And it allows you to run applications inside the storage drive and get results back out to the host without any CPU or external resources required. And we do that through our in-situ processing stack. We run a full drive OS on our devices. We have the ability to have a quad-core processor, and we even threw in some hardware acceleration because we know that you need to be able to get things done in an efficient manner. And so if you're going to store data, why not work on the data where you've stored it and stop moving it around? A great analogy we came up with from this most recently was this work from home environment that we've created. You're doing all of your work at home, all of your processing local, and you're sending your results to your coworkers. Think about that in the same frame of reference as what we're doing with your stored media and how we're deploying computational storage resources. So I've given you the who, talked a little bit about what is a CSD. So of course, the next question is, when is the industry ready? So our friends at Gartner present these wonderful reports every year called the hype cycles. This particular one shown is the hype cycle for storage and data protection technologies. Storage, computational storage, seems to fit. And as you can see here, computational storage is now being highlighted by Gartner as a technology that is ready to take off and get into the mainstream architectures. One of the unique things about computational storage is not only is it on the storage hype cycle, it's also sitting in the compute hype cycle. It's one of the few technologies that's actually crossing the boundaries of compute and storage if you were to take time and review both of these hype cycle charts. If you're interested in learning more about those charts, you're welcome to reach out to myself. I can provide you the details on it and give you some more information. But what I want to leave you with as it relates to why is and when is the industry ready for it. This is a direct quote from the business impact section of the hype cycle from our friends Jeff Vogel and Julia Parma that are the Gartner research analysts in charge of the compute and storage architectures for their global research organization. And you can see here, it says there is both a cost and time factor involved in shuffling terabytes of data around. Computational storage can provide material performance benefits for data-intensive applications, especially in edge computing, which is why we're spending time today on the edge. Combined with its low power footprint, again, carbon neutral, CS or computational storage increases the performance per watt ratio and decreases power consumption costs for applications at the edge. So when you think about this technology, there's all kinds of data center deployment opportunities with it, for sure. We can think about all unique application deployment points, but realistically, what we're starting to see is the first, I guess you would call beachhead of computational storage into the mainstream is within edge applications as it relates to AI, ML, and just simply processing closer to where we're generating the data. And there's a lot of devices at the edge that are generating data. So is the industry ready? I believe that we can see that the industry is now ready to take on and deploy computational storage, but they need to do it in a way that can be most efficiently driven by a technology that's easy to implement. So when is NGD ready to deliver? We're shipping now. But we did this with a very unique play. We said we're going to build an SSD product, an NVMe SSD. You plug it, you play it, you can use it as storage. You don't even have to compute with it if you don't want to. If you want to grow into compute, great, we can help with that. Meanwhile, we're going to give you a very cost-efficient, high-capacity, performance-optimized solution in the way of a 16-channel controller, high-capacity options, as you can see here, up to 32 terabytes in a 2.5-inch form factor, and the opportunity to turn on the compute if you wish to do so when you're ready. And one of the unique things that's coming soon from our portfolio as well, we're going to be dropping QLC drives very shortly. They're in test today, and they'll be available at even higher capacities for our end customers. So whether you're looking at an edge deployment using M.2s, if you're thinking things around an Intel NUC, or some kind of very edge-centric server that exists from some of our partners, your traditional server play, which will use a 2.5-inch drive, or even some of the new innovative form factors like the EDSFF, we have products available for you today to be able to drive these solutions. So now, who, what, and when. I've gone through that fairly quickly in just a few short minutes of this overall presentation because I want to spend time now as a developer conference showing you how we've developed solutions for our customers with these products. So where are the examples? This particular chart highlights some of the verticals that we've engaged with. So we have anything from edge gateways, the multi-access edge compute nodes, servers at the edge, and even, believe it or not, satellite engagements. We're going to talk about going to the edge. Let's go to the edge. You also have things like the autonomous market, the autonomous vehicle space, ADAS 1, 2, 3, moving to 4 and 5 over the next few years. They need local compute in that car, in that vehicle, in whatever that autonomous item is, the drones that Amazon is now flying, for example. We're still supporting things like data center deployments. You've got to eventually move the data. It can't just reside at the edge forever. We've got to have backups. Backups are in the data center. We can make that help too. All of this rolls into making everything in the world smart and more automated for our solutions. So I've got a whole bunch of different workloads, different use cases shown here on the screen that our technology's been working with today. So what I'm going to focus on now is several of these particular use cases. We have a lot of different opportunities, but I wanted to poke at a couple of them. Unique validation points for each of these ones that we've highlighted between Azure, VMware, Apache, traffic control, AWS. There's lots of different things we can do with it. The open OS that we've embedded in our devices provides the most unique and most freeing architecture available to deploy computational storage. So how about some real workloads? I'm going to talk to you over the next few minutes about a VMware deployment that we're working on. I'm very excited about this. In fact, it will be presented at a conference, VMworld 2020, the week after this event takes place. So back-to-back, computational storage, NGD Systems, we're going to make this stuff work. I have a CDN example where we're talking about customers that are trying to find a way to deliver the content to each and every one of us as we're working from home. We're enjoying things like Mulan streaming. All those types of applications still need help as well. And then we're going to get into some AI workloads. We're going to talk about AI inferencing. The concept in this particular case is a weightless neural network called Wizard. I'm going to talk about machine learning. We need to be able to do training at the edge as much as we need to be doing inferencing at the edge. Training at the edge is much more complicated in today's traditional architectures because you can't throw GPUs at everything everywhere. We need distributed training architecture. So we're going to show you how we did that with the heterogeneous Stannis network. And then finally, I'm going to end with an actual video demo of us deploying Microsoft Azure IoT Edge. And that video will actually walk you through how we create an instance and all of the parts and pieces that go with it and highlight how the benefits of computational storage can play. So up first, VMware. Virtualization is something that we all know, love, have to have. They have this wonderful platform that they built their Tanzu system on, a Greenplum database, massively parallel processing database. We also have a computational storage play with these guys because we're thinking about how do we take a rack level architecture and move it into an edge-friendly database analytics, fully fault tolerant, fully fault resilient platform. And so by working with VMware in the office of the CTO there, we took Dell platform, you gotta love it, Dell and VMware, right? Put together a couple of servers, threw in a whole bunch of our computational storage drives at very high capacities, and we're able to take a full rack Greenplum database, move it and migrate it into 2 servers, and do Greenplum analysis and even bit fusion GPU virtualization into each of our computational storage drives. So when you do need a GPU, why not virtualize it, and why not use it to help the CPUs that are inside our devices as much as the CPUs that are in the server. This will be presented in its full entirety, as I mentioned, at VMworld 2020. The session is OCTO 478. So hopefully, if you haven't already, you can register for that event for free and take a gander at this accelerated program for deployment that we did with the Office of the CTO at VMware. I'd love to share more today, but of course, I got to let it stick for the event itself for VMworld. So let's talk about a CDN. There's all kinds of fun ways you can do things with CDN architectures. This particular one is called Apache Traffic Control. It's open source, so you can go grab this graphic just like I did by simply doing a Google. What we wanted to do is work with this particular customer to get to the time to first frame. We love and hate that spinning circle on all of our streaming media services. And as you can see, bottom right in that graphic is the client. That's you and me. All of those pieces are in play when it comes to delivering content to each and every one of us. milliseconds, nanoseconds, seconds count. And so what we did is we went through the process of identifying a single stage in there that has a storage-intensive application need, help augment it with computational storage, and as you can see here, ends up with a result of 50% improvement on a single step, which makes that entire infrastructure more than 10% efficient. Now, if you think 10% isn't much, think about 5 million people hitting Netflix every minute. That 10% can be a lot. So how does it look? What does it mean to save 50% on a given step? So what we did with this is an output of someone that's doing a mock load of generating users looking for data on the top. That's the request coming from the customer. The yellow line on the lower graph represents how the current architecture was responding to that. And as you can see, as more users came on board, it took longer to find the content, where the content was, which frame rate do they need it at, and how to deliver it to the customer. What was really unique in this architecture is not only was the NGD computational storage faster, but as you can see by that bottom blue line, as more users were added, it got more intelligent. The application was able to actually get results faster over time with heavier workloads. That's computational storage at work. So yes, 50% if you look at the worst case improvement between the yellow and the blue line. Realistically, over time, it can become even more substantial than that. And this was a very small scale rollout and a very simple piece of that overall architecture that we showed before. So again, being able to deploy computational storage, sharing the resources, moving an application. In this case, they were using containers. They dropped the container into our device, hit run, it looked at all the local data, it found the content, it found the best stream, it found the right frame rate, delivered it back to the customer in a more efficient fashion than they've ever seen done before. That's what you can get from computational storage resources. So what about machine learning? This is always fun, right? We want to be able to do training at the edge. Stanis is a framework, as you can see here on the bottom right, where you have an architecture with multiple inputs and outputs, and it continually cycles through the storage architecture by reading data from the storage and putting it back into the storage devices. So I'm going to pull in a bunch of data, I'm going to train on the model, and I'm going to dump the model back into storage. What we did is we said, no, let's not do it that way. Let's have a little more unique architecture involved. Let's just move the training algorithm to the localized storage device. CPU's still got to do work. It's got to combine the models, but it doesn't have to spend the time doing the actual search and aggregation of the data in a DRAM architecture. It does it on the device. So in this particular case, we looked at 4 different neural networks that we were able to do training with. And 2 of them are highlighted here on the page. One is MobileNet V2, and you can see the training speed in images per second using no computational storage resources takes about 31 images per second, or provides 31 images per second. When you put in a rack or a full server of computational storage drives, you're getting almost 3 times the rate of performance out of that platform. Distributed training in real life at the edge. SqueezeNet is another one of them. You can see here, again, you'll notice as you training on that, the training at the host is actually getting reduced in the number of images per second over the drives being added to the system. That's because all the training is being done at the drive level. We're providing more than double the performance, and we're freeing the resources of the CPU to be more efficient at doing other work. And because we're talking about edge, and because we're talking about efficiencies, you've got to pay attention to power. In this particular instance, you can see on the bottom, as we add devices, as we get better results, no matter how much faster the results are, you're also conserving power. In this case, almost 60% of the power is saved while producing more than almost double the performance. It's a win-win. It's a TCO model play that everyone will know and love, and you can't get around. So this was done on a simple 2U server with 24 drives. Each drive was 32 terabytes. In case you're curious, that's, yes, 3/4 of a petabyte, 768 terabytes of data, all being processed in the storage devices with the host CPU going off and doing other work and getting better performance and saving power. What more could you ask for in today's architectures? So training's fun. Inferencing is, quote, easy, but let's go for it. Let's take on the GPU, for example. So you can see here, we're going to do an object tracking of someone throwing a baseball. And you can see on the bottom side, all that data is getting stored into the devices. So we're streaming off of cameras into storage, pulling it back out of storage, putting it into the host, letting the host do all the work. When you look at it from a computational storage perspective, we're not doing it that way. We're actually taking an effort to do computational storage results and have them being done. Store the data where the picture's taken, inference on it where it's taken, send it to the host, let the host merge that information so that it's able to be managed in a more efficient way. Again, all of this is about efficiencies of scale, not necessarily always performance benefit, but a way of making architectures more user-friendly and able to scale. So if we look at the graph here on the right, you can see I've highlighted some circles. In the case of YOLO, which is a traditional workload, you can see we did a GPU, a CPU, and a computational storage drive. And our computational storage drive used less energy and provided exactly the same accuracy as the CPU. Now, of course, the GPU was a little more efficient, but does your system have room for a GPU? Do you have the power for the GPU? Do you have the resources for the GPU? If we take a look at another workload, for example, in this case, the wizard workload, you can see that we did that against the CPU. Again, half the power to get exactly the same accuracy in the ability to do that inferencing. So you don't have to always use the CPU. You don't always have to use a GPU. When you've got resources at the storage device, you can actually offload the work being done into those devices, save time, save energy, and make it work. So I mentioned I wanted to talk about Azure IoT. So we worked together with Microsoft. We went into the labs there in Redmond, and we talked to the guys at the IoT show as well, and they wanted to do a little video for us. So I've taken the demo out of this video clip, which you can go and look at after the show if you'd like to do so. And it highlights how we deploy the Azure IoT Edge into a storage device. Now you may be asking yourself, why would I want to do that? Because the demo just highlights the ability to do computer vision on our drive. We actually have a customer, a telco, that needed to do a security platform. Now, I need a camera, I need to store the data that I'm getting from the camera, and I would like to use, in this particular case, Azure platform to do all my inferencing and data management. So they bought a Raspberry Pi, a USB camera, and our drive. And with that three pieces, they were able to put together a surveillance platform that can actually track an individual walking through frame, because all of the compute was being managed by our device utilizing the Azure IoT Edge and the OS that's on our drive talking to the cloud. So now what I would like to do is let you see exactly how that works and have a video clip of it showing that happening. So just 1 second, and I will get that going. For our demo today, we're going to actually show how we're running the Azure IoT Edge on a computational storage device. So first thing we're going to do is we're going to create an IoT hub device, and you can see we're generating that here. Once that's created, we actually have to do some slight modifications in this instance for the Edge agent and hub. So what we're going to do is go in and actually change the runtime settings. And the reason we have to do this for our particular implementation is you can see there that current version is actually the Intel-based platform. And so we have to copy paste in the ARM beta version to be able to actually run the device in the ARM environment. So ARM is not fully released yet for Azure IoT Edge, so we're one of the beta testers for it. And now that we've got that updated, you can see we're able to go in and actually showcase that those particular devices are there. So now we need to do the final configuration at the device level. So we're going to go into our devices. You can see two screens here. The one on the right where we're typing now is the actual device itself. So root at node 1 is we're actually within the Linux subsystem of the storage device itself, putting that connection string in. The one on the left actually represents the host platform that the device is connected to. So we're now starting the IoT Edge platform. You can see that the Edge agent has popped up. We'll do a refresh again, and you'll see that we now have the agents and the host running. And all of this, again, is being done based on the storage device itself. So there's the hub and the agent. They're both running. We're using the Docker container application to do that. You can see there's the Linux instance being published. So now what we need to do is go in and refresh, and you can see the IoT server on Azure is now seeing these products as live solutions. We're next going to create a module here, and this particular one we're going to play with is an image analyzer. So we're going to utilize the capability of our system to actually run an image analysis application from the IoT hub on the individual device itself, in this case, the computer vision application. So we're putting in all the variables that are required to allow us to use this computer vision device. And you can see we're updating all of those services and creating a container option for us so that this service will now be able to be run as you would in any other particular IoT platform. So doing all the wonderful modifications that are required, you can see we've got this now Azure IoT Edge device set up and ready to go. There's our image analyzer module. So again, it's not currently reported by the host device. So now we've got to go in and again update, and you now see the image analyzer is running again within the Linux server on the device itself. And the next step for us to do here is then now actually take advantage of having the device speak specifically to the IoT Edge itself. So we're going to tell it to go ahead and run that particular tool, and you can see that it's looking for images. So basically what we've done is we've created a file on the Linux server within the device looking for pictures. So as a picture gets derived and allowed and stuck within the particular host device, you can see this is the Azure shell running on the website of the platform. Sorry, my mouse and I are having a little bit of a fun fight. But what we're doing is this Azure device is now live. So now we're going to run that on the actual Azure side. And now we've got both event monitors running. So for this particular one, I'm going to grab a picture of the Leaning Tower of Pisa. We want to see what that picture looks like. So we're going to grab the address for that image. We don't even need the physical image. We're going to now go to our host platform on the actual server device side, and we're going to store that image into the actual application device on the right. So on the left, we're physically copying an image from the web into the storage device that's shown on the right. And you can see where it says it just found that picture. It's gone out, grabbed the computer vision application, and has found and determined that we're now looking at the Leaning Tower of Pisa. So the storage device received an image stored by a host CPU sitting perfectly idle, and yet we were able to determine and use a computer vision algorithm from the IoT Edge on the actual storage device. So we're going to do it again. We're going to grab another picture. We're going to have some fun, and this time we're going to go from Italy to France, and we're going to grab a picture of the Eiffel Tower. So again, repeat the same process. We're going to take that image. We're going to actually physically store it on the storage device. So all the host platform is doing, similar to the example I mentioned, is storing the data onto the physical device.
Yeah, it's just a regular storage device, right? Regular SSD.
So it's storing it on the computational storage device, which is shown on the right-hand side. So we're looking at an output on the right of the storage device's Linux, but he's storing that picture on that storage device. So not only is it computing on it, but it's actually receiving inbound data from the host to process. Found the picture, and there we go. We are now seeing that it's gone out, and we have an Eiffel Tower. So as you can see, we've been able to showcase a bunch of different unique workloads that are able to be derived, deployed, and utilized by computational storage. The NGD solution is a unique device in that it is an off-the-shelf NVMe SSD. We can compute with it, we can store data with it, we can manage any kind of workload that you're looking for. It's fully programmable by the user, and it's important for the marketplace today because it allows users a unique and innovative way to manage localized stored data without having to create all kinds of boxes and boxes and boxes of compute, or compose everything together in unique and unfriendly ways, if you will. Computational storage works with composable architectures. Computational storage will be deployed by various different web platforms moving forward, whether it be the cloud scale guys, second tier, third tier, CDNs, lots of unique places where these devices are being deployed, used, and are being taken advantage of by our customers. We even have autonomous vehicles, data recorders, and as I mentioned, recent engagements that are going to start putting computational storage into space. Nothing further from the edge than you can get when you put something in low Earth orbit around the planet Earth. So I want to thank you for spending time with me today. I didn't take the full 40 minutes. I didn't want to waste your time with a bunch of unique mumbo jumbo and marketing on behalf of NGD. I wanted to show you some succinct, value-added real work cases from customers, talk to you about what the technology can do for you, and hopefully you'll have an opportunity to check out our website, learn more about computational storage, and of course, pay attention to what else is going on within the Storage Developer Conference 2020. So thank you again for joining us today. I hope you have a great rest of your event, and I look forward to having an opportunity to meet you face-to-face when we're able to go back out on the road together. Enjoy the rest of the event.